In this tutorial, I will discuss how to perform a nonlinear time history analysis in SAP 2000. So the building you are seeing on the screen, this is G+4 structure, which is firstly it is analyzed by using a response spectrum analysis, and then it is designed using IS 456. Now the building is safe for the seismic action, seismic loads. Now the next stage is nonlinear time history analysis. So we know that nonlinear time history analysis is the nonlinear analysis, and therefore to perform the nonlinear analysis like a pushover analysis or a time history analysis, first of all we have to assign the nonlinearities, seismic nonlinearities, to the columns and beams. Now there are two types of the seismic nonlinearities in the modeling issue. Okay, so first nonlinearity is called as a material nonlinearity. So material nonlinearity in the sense the relation between the stress and strain across the cross section. So it is a nonlinear. The relationship is a nonlinear. So that is, it is called as a material nonlinearity. And number two is called as a geometric nonlinearity. Geometric nonlinearity is also called as the P delta effect or P delta analysis. So in SAP 2000, this P delta analysis or P delta effect, so there is one simple option is there. So while performing time history analysis, just we have to click that particular option, automatically P delta effect will be included in the analysis. So that is not that much difficult. About the material nonlinearity, in the material nonlinearity, in the sense, while assigning this nonlinearity, so there are two options. Either we can assign the material nonlinearity to the complete element, complete length of the element. So that is called as a distributed plasticity. It may be column, it may be a beam, it may be a shell element like a shear wall. So to these elements, the nonlinearity is assigned to the complete area or complete length of that particular element. So if these options we have selected, then this is called as a distributed plasticity approach. And second option is called as a lumped plasticity approach. In the case of lumped plasticity approach, the nonlinearity is assigned to the element in the specific zone of the element. For example, to the beams and columns, the material nonlinearity as far as the lumped plasticity is concerned, is assigned at the ends of the element, So why at the ends of the element? Because if we see the past failures, photos from the past failures, we have seen that due to the earthquake, many elements like a beam and column then had been failed at the ends only. So that is the one reason why the nonlinearity is to be assigned at the ends. So the ends are very critical. So at the ends, under lateral loading, the flexural stresses as well as shear stresses are also maximum. So therefore these critical locations for the failure under earthquake is since it is the ends, so therefore the material nonlinearity are assigned at the ends only. Now to assign the material nonlinearity at the ends, so this is called as a lumped plasticity approach. So we have to assign some hinges. We have to assign some plastic hinges. Now to assign the plastic hinges, again, there are two ways are there. First is that the user can evaluate the properties of this material, of these plastic hinges. So this is, if this option is there, it is called as a user defined plastic hinges. And second is called as in SAP 2000 library. So there is some ready-made hinges are there. Okay, so what is called as auto hinges. So you just select that particular element and then assign the auto hinges which is available in the SAP 2000. And this is very simple approach. And many researchers also worked on this, and it has been found that the user-defined hinges and the auto hinges, this gives nearly the similar results. And it is a time saving also by assigning a auto hinge. It is a computationally very efficient. So this particular approach we will adopt in this case. Now first of all, we'll assign the auto hinges to the beams, all the beams. So first is select all the beams. So the option is, the commands are select then properties, and the frame section. And then, so these are the different categories of the beams. Already it is defined. Okay, so select all. At one click, we can select all. Then this. So all the beams have been selected at different floor levels. Then go for next is assign frame, and hinges. Assign frame hinges. Okay. Now we will assign the auto hinge at the ends. So relative distance is, suppose the joint I and joint J, I and J. So here, so we'll assign the first hinge at a relative distance equal to 0.1 location. That is, this is the first hinge. Okay, now go for the second. So it is this is a concrete beam. So select a concrete beam. Okay, now whatever these auto hinges, so auto hinge in the sense there are some properties also. So which properties? So, and these properties are the cross section specific. That is, at that particular cross section of the beam, the cross sectional property in the sense, what is the sectional dimension, what is the grade of the concrete, what is the grade of the steel is there, what is the amount of tension steel, and the on that, and what is the value of shear force on that, the material, the hinge property also depends. So therefore, on this particular material property at that particular cross section, the relation between the moment and curvature depends. Okay, and afterwards it also calculates the moment rotation relationship. And all this now to evaluate these particular properties, to evaluate all these properties, very important is that there are some parameters required. So all these parameters in this particular SAP 2000 library, so this is taken from this particular code. So SAP 2000 automatically extract the parameters from ASCE 41 and table number 17. Okay, so that is the next thing. Okay, now we are assigning the non-linearity to the beams. So what is the degree of freedom? So first is degree of freedom for the beam, it is M3. Okay, then next is also to estimate to calculate the properties of this plastic hinge, the shear force value is required. Now here, so there are two options to calculate the shear force. First of all, whether the shear force, it will be case combinations. So that is, so any whatever the predefined load combinations are there. So do you want to calculate the shear force value from the predefined load combinations? Or second is, or do you have any equation, some equations are there to calculate the shear force? So in this case, we will go for the first. That is, already we have defined one load combination, that is dead load. Already we have defined the dead load load combinations. I will show afterwards this particular load combinations. And then, so under this load combination, or due to this load combination, whatever the shear force, okay, so we are giving the instruction to the software that use that particular value of shear force for the calculation of the properties of the plastic hinge. Okay, then, so this is the next is the transverse reinforcing is confirming. So if this particular design, okay, so whatever the design, if it is ductile detailing, or in other way, if this particular frame is a special moment resisting frame, if it is a special moment resisting frame which is designed for ductile detailing, then in that case select this particular option. And if it is an ordinary moment resisting frame in which the ductility provision in the form of reinforcement detailing is not done, so then uncheck this particular option. Okay, then also there is one reinforcing ratio required. So this ratio we are this thing, so SAP 2000 automatically calculate from this particular, from current design. Okay, so it will take so already this, as I said, that is already this building is analyzed and designed. So analysis and design results are already is there. So whatever the required parameters, it will take from those analysis results. Okay, and then click on OK. Now this is, then second hinge we will assign at a relative distance equal to 0.9. So add this. So the same this thing are there, the parameters are there which are already just designed for a distance equal to 0.1. Okay, then say okay, then apply and say okay. Now see, okay, now these are the different hinges we are seeing here. So for example, this beam, so this is the first hinge and this is the second hinge, and these are the numbers. It is 178H1, this is the number of this hinge, 178H2. So these are the different hinges. Okay, so this is a, now as I said, this is the hinge, the hinge properties at different locations are different because the section properties are different because of their different locations. So these are, we have in this way we have to assign the hinges, plastic hinges, to the beam. Now we'll go for the how to assign the plastic hinge to the columns. So first of all, select the column, all columns. So select, then properties, frame section, and then column. Select and okay. Select and okay. Okay. Then assign frame and then hinges. Okay. So first location is 0.1. Then add this. Okay. Then select here concrete columns. Okay. Now carefully define the degree of freedom. So degree of freedom for the column, it is a PM2 M3 column we design for axial load plus biaxial bending. So choose this option, PM2 M3. Okay. Then P value, axial force value also it requires. So axial column loads. So again we'll instruct from that is take the value from the case combination, that is dead load nonlinear. Okay. Then other parameters as it is, keep a default whatever the parameter and say okay. So this is at a 0.1 distance, then next hinge at a 0.9 distance. Okay. Then these are the same parameters as a 0.1 distance. Okay. Then apply and this okay. Okay. Now these are all the hinges we are seeing for the columns. Okay. So this is, in this way we have to assign the material nonlinearity. So which option we have adopted? We have chosen an option of a lumped plasticity approach. So in this way, in the SAP 2000, so this is the option. This is the option of a assigning the nonlinearity, material nonlinearity using a atto hinge. Okay. Then just before to go for the time history function, I will show the dead load nonlinear case. Okay. So here already that particular case is defined. Okay. So here the first case, whatever you are seeing is, okay. So this case is there. It is a dead load nonlinear. So it is predefined. Okay. So how it is? Just I will modify this. We will modify this particular case. Okay. Now here, this is the first is the title, give as a dead load nonlinear, and this important is static nonlinear. Go for static nonlinear. Okay. Then in this particular table, okay. So already whatever the different loads that are assigned on a this particular building, on various elements of a building. So which loads? Dead load by default is there. Then brick wall, external brick wall, internal brick wall, then parapet wall is there, then floor finish is there, then live load on a floor and live load on a this thing roof is there. Okay. So these loads we have already defined. This is already defined. So therefore, so all these loads which are permanently acting on the structure, all these loads should come here. Okay. So in this way we have to assign this particular dead load nonlinear case. Now time history analysis is again it is a two-stage analysis. So first of all dead load nonlinear case will be analyzed. Case will run, and at the end of dead load nonlinear, whatever the stiffness of the structure, that stiffness of the structure will be the beginning stiffness for the time history case. So therefore, it is called as a two-stage analysis. Just I will repeat. Two-stage analysis means, first of all, dead load, this particular case, whatever you are seeing on the screen, on dialog box. First of all, dead load nonlinear case will run. Okay, dead load nonlinear case will be run. At the end of dead load nonlinear case, whatever the stiffness of the structure, that stiffness of the structure will be the beginning stiffness for the time history analysis. Okay, so this, therefore, it is called as a two-stage analysis. And because of this, because of that is, after the analysis of dead load nonlinear, whatever the shear force is there, so that shear force, it actually the software utilizes to calculate the value of shear force while evaluating the properties of the plastic hinge. Yes. Now, just we'll hide this particular hinges. So just here one option, it is a, just click this option, show undeformed shape. Okay, so it is a, when you click this, okay, so all the hinges, just it is hide. Hinges are there, but this, it is just hide. Then now we'll define the time history function. Okay, so time history function we will define like this. So it is define function and it is time history. Okay, then so here in SAP 2000, there are some inbuilt time history records are there. So we'll choose the we'll choose one the ground motion record from the SAP library. So it is from file. Okay, you just add this. Okay, add the function. And now just browse this. Okay, browse. Now here it is a time history function. Just click on a time history function and then open. Okay, so these many ground motions already are there in the in the SAP library. So I will just click the first one. Okay, so open. So there is an option that is suppose that is in SAP 2000 there are some ground motion records are inbuilt, or in peer strong motion database you will get a number of ground motion records. So you can download the ground motion record from the peer strong motion database also, and then also we can use that particular ground motion for the time history analysis. Then now first of all we'll view this particular file. Just click on this. So it is in the notepad. Okay, it is in the notepad. So first 4 lines, 1, 2, 3. Okay, so first 3 lines are just the information. Okay, these are called a header lines. So these header lines are required to skip in the analysis. So these 3 lines are there. And next now, so in one line, how many number of records, number of readings? 1, 2, 3, 4, 5, 6, 7, 8. So in one line, there are 8 records are there. 8 readings are there. Okay. So here header lines, initial header lines, how many to be skipped? 3. Okay. Then prefix character per line to skip. Prefix character in the sense, in some records, in some files, so there are some characters like comma or colon, such characters are there, prefixes are there. So in a line we have to just count it, and suppose there are 2 are there, you just put here the value of that many number, how many prefixes are there. So in this case, in this text file, there is no any such prefix. So therefore it will be 0. Okay. Then number of points per line, how many are there? There are 8 are there. Okay. Then here give the name to this particular time history record. So it is a, what is the name of this? It is a Altadinea. Altadina is the name of this ground motion. Okay. Then, so these readings are at the regular interval of 0.020. 0.020. So here The readings are the 0.02 seconds. Okay, and then you just click display the graph. Display the graph. Okay, now this is actually the ground motion, right? So this is, in this way we have to define the function and then say okay, this okay, and then okay. Next, now we'll define the load case. We have defined the function just now. Now we'll define the load case. So define load case, define the load case, and in this add new load case, add new load case. Okay, now before that we must know what is the time period of this particular structure. Why it is required, I will explain afterwards, but we require the time period. So for that you just run the modal analysis, run the modal analysis and get the time period. What is the time period in X direction and what is the time period in the Y direction? In the fundamental mode, obviously in the fundamental mode. Okay. So it is display table, then structure output, then modal information. This is the modal information. Okay. Now what is the time period? For the first mode time period is 0.53 and this is in X direction. First mode is in X direction, time period is 0.53, and second mode is in the Y direction. Okay, it is in the Y direction and time period is 0.80. Okay, now we'll export this into Excel because this is information we require afterwards. So export into Excel. Okay. Then unlock the model. Okay, now we'll define the load case. So define load case, then add new load case. Now we'll perform time history analysis in global X and global Y direction. So first is time history in X direction, time history in X direction, give the name. Next, it is a load case type. It is a time history. Load case type, it is a time history. Okay, now here. Now these are the different options of performing time history analysis. So time history linear also we can perform, non-linear also we can perform, then modal and direct integration method. Okay, so non-linear we can also perform non-linear modal time history analysis. So it is also called as a fast non-linear analysis, fast non-linear analysis. But actually the non-linear modal type, okay, or linear modal type. So this actually type of the time history analysis will not give the failure mechanism of the structures. The hinges will not develop. Where the hinges develop, so that information will not get this from this particular type of the analysis. So to get a information about the yielding of the structure, after yielding, what is a capacity of the structure, where the hinges have been formed, and how the hinges, where the hinges have been formed, how many hinges have been formed, and what is a progressive type of the failure, that is in which element the hinges have been developed first, then in the second, then third. So which are the, what is the progressive type of the failure? To know this, we have to go for the option non-linear direct integration. So go for, it is a non-linear direct integration method. Okay, and this is the option to define the P delta, that is what is the geometric nonlinearity. So geometric nonlinearity, in the sense it is a P delta effect, it is the relation between strain and displacement is a nonlinear. So here in this tutorial we will include the effect of the P delta. So just click this Okay, so automatically the effect of it will be included. Okay, now as I mentioned that time history analysis is a two-stage analysis. So therefore, first of all, you just click the second option. Click the second option. So continue from the state at the end of nonlinear case. So as I mentioned earlier, that is, first of all, dead load nonlinear case will run, and then this time history analysis will continue at the end of the dead load nonlinear case. So therefore, go for this particular second case. Okay, now in the load applied case, first is load applied acceleration type. So this is in u1 direction. So the function is already, it is defined the function. So it is a Tandiya. Okay, now scale factor. This is very important. Now scale factor, how much scale factor to be implement? So for that, you just check the unit. Okay, what is the unit of this particular? So all these records are in the unit of centimeter per second per second. Sometimes all the readings are expressed in terms of G. So if the readings are in terms of G, then the scale factor will be equal to 9.81. 9.81. Now in this case, it is in terms of centimeter per second square. And what is our model unit? It is in the meter. Model unit, it is in the meter. So therefore, all these readings, it is required to convert into meter, right? So therefore, divide each reading by 100. So it is 1 divided by 100, it is 0.01. So is the scale factor. So therefore, here the scale factor will be 0.01. 0.01. You just add this. Okay, so this is our scale factor. Okay, now number of output time step. Again, see this thing, the notepad, the file, and in this, how many number of readings are there? Okay, how many total number of records? So these are the 200 readings are there, and 200 readings, and at the interval of 0.02. Okay, 0.02 means how many seconds it is actually this time history. So it is a 2000 readings are there, 2000 readings, and these are taken at the interval of 0.02. Okay, so it is a 40 second. So this earthquake record is of 40 second. Okay, so therefore, so in the output time step, actually, so this is just a output time step is there. So here we can define as a 2000 number of readings, and output time step will define as will keep as a 0.02. Okay, this is the second. Then about the damping. Okay, so click on modified and show. Okay, now there are to include the effect of damping in the analysis. So there are three options we have. So in the SAP 2000, so that is, first is a direct specification. Okay, so that is this mass proportion coefficient and stiffness proportion coefficient. Directly substitute the values here. Second, damping, the software automatically calculate. We have to just specify the damping by period, or we have to specify the damping by frequency. Okay, now, so that is here we will choose the second option. Okay, so damping by period, just click on damping by period. Okay, so it will calculate the mass proportion damping and stiffness proportion damping. So just we have to define here the time period of the first mode and second mode. See, first mode time period. Now from the modal analysis, we come to know what is time period of the first. 0.536 is the time period of the first mode. You just include here first mode, it is a 0.56. Okay, so this is sufficient. 0.536. 0.536 is the first this thing. And what is the second mode time period? In the x direction, this is important. In the x direction, so this is x direction, first time this thing, and second mode in the x direction is this. This is the second mode. And what is the time period? It is 0.70. It is 0.70. It is 0.70. Yes, okay. And the constant damping, it is 0.05. Since it is a RCC building, it is 0.05. Okay. And then just click it. And then recalculate, you click here, recalculate coefficients. Okay, so it is these are the coefficients calculated by using the data from the modal analysis along x direction. Okay. Then second, time integration method. Okay, so this is to solve the algorithm. These are the options available in the SAP 2000. So it is a default option is the Hilbert-Hughes-Taylor integration method. So let it be. Okay. And third option actually should be implemented if the time history analysis is not run because of some the program error comes. Then in that case only, so the all it is a editable. So we can make certain changes, and then the program will calculate the time history analysis. The analysis will complete. Say okay. So here in the third option, do not make any change. Keep the parameters as it is. So this is the first, that is in x direction. In this way, we have to define the load case time. Load case. Then again in the y direction. So you just copy of this, add a copy of the load case. Then this is a time history in y direction. Time into y direction. Only here instead of u1, it will be u2. Modify this. Okay. Then here there is no change. Only damping case we have to make certain changes because now the time period in y direction. So this is the y direction. Okay, so this is the first mode, 0.49. Okay, 0.49. And second significant mode is this. Okay, 0.16. So 0.49, 0.49 and 0.16. Okay, these are the two modes. 0.49 and 0.16. Okay, constant damping 5%. You just recalculate it, then okay. Okay. Okay, now these are the two load cases where we have defined just now: time history x direction, time history y direction. Okay. Then, okay, now we'll run the analysis. Actually, push work case is previously defined, and therefore, so it will complete the push work analysis also, and then time history analysis will start. So instead of that, we'll cancel the push work analysis case. We'll just stop the analysis. Yes. Okay, now here, while running this, first of all, make it as a do not run. All this is, and for time history analysis, first is this case, then modal analysis. These are required. And then time history and time history. So these are required. Okay, then run now. But as compared to pushover analysis, the time required for time analysis, time history analysis is more. Definitely, it will more, because so many hinges we have defined, and the equation of motion mx dot double dot plus c into x dot plus k into x is equals to ground motion component. This equation actually it solves at every the hinge point, and therefore it takes a time. So if the building model is very a large model, then there's these many number of hinges, so it will take more time. So therefore for time history analysis, so it is computationally expensive, and therefore we required some this thing one some advanced this thing level of computer. So maybe the speed will be more. So here we will not wait until the complete analysis. Just I want to demonstrate how the function to be defined, and after the analysis which results are to be seen. So therefore at least we'll wait for the complete analysis in the x direction. Now it is a we can see here we are seeing that is 47% time history analysis in x direction has been complete. Now 50% completed. So we can see the status, that is how much part of the analysis have been completed. So here also we can see we have totally there are 2000 number of readings are there. Now out of that nearly 1200 have been completed. Okay, and now 75% analysis in x direction has been completed. So therefore we'll see the result up to this, because it will take a time, more time. So we'll not wait for this thing. Okay. Now first of all we'll see the deformed shape under time history. So here display, then deformed shape to see the hinge status. Okay, now time history in x direction. So we can see the deformed deformed shape right from 0 second. So this time history is for 40 seconds. Now suppose after 10 seconds, say after 10 seconds, what is the position, how many number of hinges have been developed. Okay, so if we see the 3D view, see these many hinges have been developed, and all the hinges are in the immediate occupancy state. So here this is status bar. So green, everywhere it is a green. That means after 10 seconds hinges have been formed, but it is in the immediate occupancy state. That is, it just crossed the yield stage. Then so in this way hinge status we can see. Then second is that now to see the displacement of different modes, so go here, show tables, show table, and here the joint output is there. Okay, joint output, and to see the this thing displacement. Okay, so here a joint displacement, go select for the first option, select a load case as the time history. Okay, and then say okay. Okay, so these are the joint displacement at different points. So this is a time history case in x direction. Okay, so it is a maximum and minimum. Okay, so this is a so joint numbers are there. So text joint number 1, then joint number 2 is there, then joint number 3 is there, then joint number 4 is there. Okay, so these many are there, and this is the maximum, what is the displacement at that point. Okay, and minimum, what is the displacement at that particular point. So this information will get from this particular table. So maximum and minimum in the sense In one direction, it is a cyclic type of the force. It is cyclic type of the force applied to the structure. So in one direction, it is calling as a maximum. In other direction, it is called as a minimum. Okay, so this is a, so therefore minimum readings you are seeing in the minus. Minimum readings we are seeing in the minus, in the sense it is in the opposite direction. So this is a displacement in x direction. Y direction, it is almost 0 because this is a time history in x direction. So this is in the z direction, and this is the rotational rotational displacement. Okay, rotational displacement with respect to x, with respect to rotation, with respect to y, rotation with respect to z. So this is in the radians. So results, we can, this table we can export into the Excel, and from this we can calculate the drift and all this. So this is the second reading we can see from the. Then third is that, okay, third, now we can see the floor spectrum from this. So display, show a response spectrum. Okay, show response spectrum. Before that, suppose, what is this? Just click this. What is the node number? It is a 78. Okay, this node number is 78. Just remember this. So display and then show a response spectrum. Show response spectrum. So here it is a node number is just 78. Okay, 78. And these are the different damping values. Suppose we required only the damping for the 5%. If the damping is 5%, then what is the flow response spectrum? So that we'll see. So just say done. Display the curve. Joint number 78. Joint number 78. Global x direction. Then say done. Okay, it actually it is showing some response spectrum plot of a 78, joint number 78. Just I will in other way I will try. Just required to define the joint number, add this. Then here it is a display curve. Here option is there at the corner bottom. Here the option. Just click on this. Okay. Okay. Now this is the response spectrum or the floor spectra of joint number 78 for damping 5%. So we can change the damping also. So it is frequency on x-axis and pseudo spectral acceleration on y-axis. Another parameter also we can choose. Okay, so here suppose on x-axis we choose as a period, then axis type either we can keep as a log or arithmetic. Okay, then on y-axis it is a value on y-axis. This is suppose spectral displacement will keep as a spectral acceleration. Okay, so y-axis spectral acceleration and x-axis, so it is a the period in second, and damping will be 5%. Then just display this. So this is the, if the parameters are changed, x parameter, y parameters are changed, just titles are changed, then it will be the plot will be like this. So that is, this is the joint number 78. If we change the joint number, then again the it will represent the different graph. Okay, so this is the second result we can see. Next is display here show plot function. Okay, show plot function. So in the dialog box here, okay, So define plot function here, define plot function. Okay, so here different options parameters are there. Suppose we want to see the joint displacement. We want to see the joint displacement. Okay, and just add this joint displacement, add this. Then displacement in vector is a displacement in x direction. Okay, so here in ux displacement, say okay. Okay, node number, it is required to define node number. Okay, so we'll define the node number as I say 78. Okay. Okay, so this is this okay. Okay, now here this joint 78, just select it and add. Okay, now it will take a, on vertical axis, it will take a joint 78 displacement. Okay, and with respect to time, and then say display. Okay, now this is a plot of time on x-axis and displacement on a y-axis. So here, so okay, so that is, so this is time in seconds. So 4 seconds, 8 seconds, this is the time. 8 seconds, this is time. Okay, so the time history is actually 40 seconds. So that is, we are seeing that. So in between, say 4 seconds to say 10 seconds. In between this, the amplitudes, the displacements are higher of point number 78, and somewhere this is gives the maximum displacement. At this particular time, this displacement is maximum. So at the, in this way, we can see the displacement plot for any joint or for any node. Okay. Then next is another plot function we can select as a, so define plot function, then go here. So suppose a base function, okay, base function as this. Suppose base shear, what is the variation in base shear in x direction? So what is the plot of this? Okay, then you just remove this part of it. Then base reaction. Okay, so what is the, now we'll get a plot of base reaction versus time. Then display this. Okay, now this is the base reaction in x direction. So in y-axis, and in x-axis it is a time. So we are seeing that the maximum base reaction is equals to 1 into 10 to the power 3, and it is in kilonewton. This is the maximum base reaction. Okay, so similarly, we can see the other plots also. Other anything, base function, joint displacement, frame forces, and then shell forces also. Then load functions, just we'll see what it is there in the load function. Okay, these many are, so different loads we have defined. So what is the variation? Actually, in time standards, this load function is not important. A base, that is a response spectra, what is called as a floor spectra, then a variation in the displacement, then variation in the base reaction. These are the important results to be obtained. And then next is the hinge status. Just we have seen this. So these are the important results to be seen